Hello, my name is Mike Courtney. I am Senior Researcher at DTU Wind and Energy Systems. In this lecture, we will investigate how we measure the wind. After this lecture, you will be able to explain the difference between in-situ and remote sensing, list the main in-situ sensors for measuring wind speed and direction, and describe how these sensors function. So what do I mean in-situ versus remote? For many years, nearly all the wind measurements in wind energy were made using masts with instruments like anemometers mounted on the masts, as we see in the background here. Nowadays, there is also the possibility of measuring wind remotely using sensors known as LiDARs. This is known as remote sensing. Remote sensing is becoming quite widespread, especially from offshore measurements in wind energy, where it can be extremely expensive and almost impossible to build masts. This lecture concentrates on in-situ methods. In another MOOC lecture in this series, you will find lectures on remote sensing instruments. There are three main in-situ sensors that we're going to talk about today. Anemometers, commonly referred to simply as cups. Sonic anemometers, also commonly shortened to sonics. And lastly, wind vanes for measuring the wind direction. So let's look at these three sensors, each in turn. Anemometer is a very well-known and very widespread instrument and the main instrument for measuring wind speed in wind energy. We have a rotor that's blown around by the wind. It's connected to a spindle in the body, and that drives a mechanism in the bottom that, through some electronics, generates a pulse train that gets collected from a connector in the center of the instrument. And then we determine the rotor speed, the speed of rotation of the instrument, by looking at the frequency or the period of the pulse train. But how is it that the rotor actually turns? Why is that? Well, let's have a look and see the drawing here. We have the wind coming from the right. The wind will actually generate different drag forces on the different cups in the different positions as the anemometer rotates. On this cup here, the drag will be highest, and it will be much lower on the cup that's returning here, simply because this is a more streamlined form. So D1 will be somewhat larger than D2, and that means that there will be a moment driving the anemometer around. When that moment reaches the friction moment acting against the rotation, then the anemometer will rotate at that speed. So for a given wind speed, the rotor turns at some particular angular speed, omega. The relationship between the wind speed and the rotational speed is in fact very linear. But due to the very complex nature of the aerodynamics, it's almost impossible to calculate theoretically. So instead, what we do is we put the anemometer in a wind tunnel and varying the wind speed of the wind tunnel and measuring with a pitot tube. Here we have a pitot tube measuring the reference. We can then create a transfer function for the instrument. Here you see a plot of the frequency measured from the signal coming out of the cup and the reference speed at the side. And you can see then we do a simple linear regression, and you can see we get a very linear fit. Here and here we have the transfer function. And notice that we also have an offset, and that corresponds to the small amount of wind that we actually need just to get the cup to start, to overcome the initial friction in the system. So that was the cup anemometer. Now let's look at a sonic anemometer. This is, as you can see, a lot larger, a lot heavier, and it uses a lot more power, and it's actually considerably more expensive than a cup anemometer. So we'll look at and see why we should use this instead. But let's also first try and work out how this actually functions. You can see here that we actually have 6 probes, but if we look carefully, we can see that it's actually 3 pairs of 2. This is a pair here, this is a pair here, and this is the 3rd pair here. If we now look at the first pair, let's see how the wind speed is derived. What actually we're doing is, as the name sonic implies, we're using sound. We're sending a sound pulse from this transducer to this transducer. So then we measure this time. That's the first step. Then we do the reverse. We send a sound pulse in the other direction. We send it back to where it came from originally, and also measure this time. So T1 this way, T2 this way. Now imagine if the wind is actually blowing in this direction, from here to here, the sound will actually go faster this way and slower this way. And that's exactly what we need to actually calculate the wind speed. By doing some algebra that I even can manage to do myself, we can quite easily work out that the wind speed component along this line, which we call Vp, is equal to half the distance between the probes multiplied by the difference in the reciprocal of the times. So actually a very simple relationship. So then, once we've done this for one pair of the transducers, then we can do it for the other 2. It's actually a computer in the instrument, in the base of the instrument here, that controls all this and does all the calculations. We do it for this pair, and then we do it for this pair. So then we have the wind speed in 3 different directions. You can see they're not actually at right angles to each other, but then that's a simple transformation, coordinate transformation, and then we actually get 3 wind speeds in an XYZ coordinate system. Z points upwards, gives us the vertical wind speed. Y traditionally points to the north, so you can see there's a north arrow on the side of the instrument to tell us how to align the instrument when we put it on the mast. And then of course the remaining, the x-axis, will be perpendicular to that in the horizontal plane, so pointing to the east or to the west. So since we now have 3 components, we have a true vector. We have both the magnitude of the speed, but we also have the direction of the wind. And that means that we can use the sonic anemometer to measure both the wind speed and to measure the wind direction, and even to measuring the tilting angle, so the angle of the wind to the horizontal plane. For this reason that we have the 3 components, and also because the sonic actually measures quite fast, so we can make these measurements at about 25 Hertz, this model, and also because this distance is fairly short, this sonic anemometer, any sonic anemometer, is actually very, very good at making turbulence measurements, and that is one of the main purposes for using a sonic. You get a great deal of insight about the nature of the wind from a sonic anemometer. Lastly, let's look at the wind vane. If we don't have a sonic anemometer, and often we have a simple system only with cups and vanes, then of course it's also really important to measure the wind direction, in fact to measure the wind direction at several heights. This is very familiar to most of us. We see something similar on houses around, and they've been around for many hundreds of years. So we have a vane that somehow, we will look closely in a second about why. This is connected to a potentiometer, a variable resistor in the base of the instrument, and that provides us with an electrical signal here that will actually tell us where this vane is pointing. Now let's look at how this actually works. If you imagine the wind coming towards me this way, and the vane is slightly displaced from that direction, then we'll be actually generating a lift and a drag force, just as on a wind turbine wing or on an aircraft wing. And both those forces, the L and the D, they will be acting to move the vane, to realign the vane to the wind direction. like that. It turns out that this is what we call a second order system, and it will actually slightly overshoot a few times before it really settles to the actual wind direction. Wind direction has a discontinuity because we measure cyclically between 0 and 360 degrees and then back to 0. Then we have this problem that sometimes we will have a discontinuity between 359 degrees, say there, and 0 degrees there. So when we look at a time series of wind direction, they can sometimes, when we're in this condition, they can sometimes look pretty strange. So you can see in this case where the wind is between something like 355 degrees and 5 degrees, and it keeps jumping between those. It looks as if the wind direction is changing very rapidly, but that's not, of course, the case. So care is needed when calculating mean wind directions. There are, luckily, good methods to enable us to do this correctly. But also, mechanically, electronically, we have a problem because, as I said earlier, we have a potentiometer in the bottom of this, and in order to generate the necessary voltage around that potentiometer, then of course we need a gap. And that means that in fact we can only measure the wind direction in something like 358 of the actual 360 degrees. We have this north gap where we're not actually able to measure the wind direction. Usually we make sure that the so-called north gap actually points in a direction where the wind comes fairly infrequently, so it's not too much of a problem. And here you can also see how we're actually getting the signal from this, the direction from the signals. We actually have two voltages. We apply a voltage across the whole in potentiometer, Vs, and then Vw here, wiper, V for wiper, we measure the voltage between the negative terminal and the wiper. That tells us how far around this pointer actually is. And of course the pointer is connected to the vane of the instrument. And then the wind direction is a very simple ratio of these two voltages multiplied by 358 degrees. So, in summary, in this lecture, you have learnt the difference between in-situ and remote sensing, which in-situ sensors are used for measuring wind speed and wind direction, and how these sensors function. Thank you for listening.